the Doppler effect. Last lesson of Physics 20, great lesson. Unfortunately, it doesn't come back in Physics 30, but the Doppler effect is another one of those important concepts, not just for sound. So the Doppler effect is when you think you hear the pitch of something dropping, and you do, the pitch is dropping, but not from the source. So for example, when a car goes by here, meow, when you hear that, if a car is blowing its horn, and the pitch drops, it's not because the pitch of the horn is actually dropping, it's because of the Doppler effect. And this is another one of those lessons where you have to watch a lot of videos. Watch the Big Bang, Google the Big Bang Theory, that television show Doppler effect, and you can watch something humorous about that. I'm going to demonstrate the Doppler effect using this one. And in this video, we've just got a source. The red guy here is the source. So he's going to emit a frequency of sound. And the green guy is going to move towards it. And I'm just going to go ding, 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 ding every time a sound wave hits the green guy. And so the green guy, he's going to perceive the line. If he's moving, the sound waves are going to hit him faster or slower depending on which way he's moving, and so he's going to perceive the frequency of the sound to be different than the red guy who is emitting the sound. So here's how this works. So if I'm going ding 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 and it's getting faster, it means you're hearing a higher pitch. Here we go. Here we go. Ding 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 ding. Oh, I love that video. It's so elementary and yet so effective. So as you saw from watching that video, when he's stationary, he's hearing the same frequency as the red guy. But when he's moving towards the red guy, these sound waves, because he's moving towards him, are hitting him faster. So he's heard there's less time in between each ding, and therefore he hears a higher pitch. As he's moving away from the red guy, he's moving away, he's moving this way, the sound waves are hitting him much less frequency, and so he hears a lower pitch. And that is the Doppler effect. It is the apparent change in frequency when the source and the observer are in motion relative to one another. And it's not just important in sound, it's important in, this works for light also. And this is why we presently believe very strongly that the universe is in a great state of expansion. Because when we look at the stars, we see everything being redshifted. We'll talk more about that later. But what it means is everything that looks red in the universe is moving away from us, and everything that looks blue is moving towards us. And most things in the universe are redshifted, which means the universe is expanding. Okay, so here's the Doppler effect. I just described it. There's a whole bunch. You should Google some video or go on YouTube, watch some videos. It is the apparent. Okay, we just discussed all this, and I did this example of this blah 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 blah. Here it is. Okay, and then you can watch all these videos. There's great videos on sonic booms. If you have a whip and you make the crack of a whip, is actually the end of the whip breaking the sound barrier. Okay, and onward, and here, so the Doppler effect is the apparent change of frequency when the source and the observer are moving relative to each other. And here is the formula for the Doppler effect. And this works for sound and it works for light, and it is the frequency equals the velocity divided by the velocity plus or minus the velocity of the source. And the velocity in this case is going to be this, since we're talking about sound, is going to be the velocity of sound, the speed of sound. Okay, if we talk about light, it would be the velocity of light. And then you've got this unusual thing here, it's plus or minus, and the plus or minus is used to indicate if you're moving toward or away from the observer. And before you look at your notes, don't cheat, don't cheat. Before you look at your notes, figure out which is which. Okay. Oh, we've got a plus or minus. This is the frequency of the source. So let's say the source, you're standing on the street and you're going la, 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 and the frequency you're making is 440 hertz. 440 hertz, because that's what orchestras in North America tune to. 440 hertz, A, this is the note A. And you go la, 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 and you're just standing still, and somebody's moving towards you. If they're moving towards you, that's the frequency is going to appear higher to them. So this is the frequency that you're making. The frequency that the person is going to hear if you're moving towards them is going to be higher. So they're going to hear, they might hear 470 hertz. So they might hear a pitch that's higher than A. So for this number here to be bigger, should this be a plus or a minus? Think about it. Think about it. And after you've thought about it, you're going to come up with the obvious conclusion that if we want this number here to be higher than that number there, then we need this number here on the bottom to be as small as possible, and therefore it's going to be a minus if the objects are moving towards each other, relatively speaking. If you're moving towards, or if that person is moving towards you, or you're moving towards that person. So as objects get closer, you use the minus. As objects are getting farther away, then you use the plus, because then this number here is going to get bigger, and it's going to cause this number here to get smaller. So if you didn't get that, then just read this. It says it right there. If the source is moving towards you, use the minus sign. If it's moving away from you, use the plus sign. But please, use common sense. If something's moving towards you, you're going to hear a higher frequency than what the actual source is. So you should get a higher answer. All right. Here's our example. A siren is making a sound at a frequency of 8,500 hertz while driving down the street. It is on a cold day and the speed of sound is only 300 meters per second. If the ambulance approaches you at 25 meters per second, determine the frequency you will hear. So the 8,500 is the frequency of the source. That's the ambulance. It's driving towards you. So you are going to hear a frequency that's higher than 8,500 because it's moving towards you. The sound waves are hitting you at a greater frequency. The speed of sound in air on that day is a very slow 300 meters per second. And then the speed of the source is 25 meters per second. And again, the only difficult part of this question is deciding whether it's a plus or minus. And since it's moving towards you, you're going to use the minus in the Doppler effect formula, which is and then it's just a matter of plugging the numbers in. It's going to be 300 divided by 300 minus 25 times 8,500. Make sure you do everything in your brackets and the calculator first. And then multiply it by 8,500, and you should end up with, let's write it down. You should end up with, I think it's 9,273. I might have written that down wrong, so please check that on your calculator. 9,273, something around there. And the answer was higher, and we knew it should be higher. And then B says, if it was moving away from you, it's exactly the same question, except for now the minus becomes a plus and the 25 becomes a 20. Oops. And for that one, you end up with a lower number, 7,846 hertz. Okay, and that is it. That is the end of the Doppler effect. And as I said, this works with light too. And because light, we won't do this in detail, but because light has a fixed velocity, 3 times 10 to the 8th meters per second. Well, let's do it quickly. Frequency equals 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second minus. So let's say if we think that the universe is moving away from us, right, as in redshifted, then this should actually be a plus. So let's say the universe is expanding at a rate of, I'm just totally making up numbers, because there are lots of theories of saying the universe is expanding at a speed that's faster than the speed of light, which is mind-boggling in itself. But let's just say you pick a random number, like 10 to the exponent 3, 1,000 meters per second, which it's not. That's not the answer. Times the frequency of the source here. So the frequency of blue light. Or let's actually not even go. Let's just say the frequency of the source here. So what's going to happen here is that this number here is going to be smaller. And if this number is smaller, in other words, the perceived frequency is smaller, then according to this formula, if the frequency is smaller, the wavelength must be longer. And once you get into physics 30, you're going to learn, oops, that red light has a wavelength of 700 nanometers, and blue light has a wavelength of 400 nanometers. So red has a longer wavelength, therefore it has a smaller frequency. And that's why we call everything that's redshifted in the sky, when we look at stars through telescopes, everything that's redshifted is moving away from us. Everything that is blue shifted is moving towards us. And the majority of things that we see in the night sky are, or in the universe, are redshifted. Hence our belief that the universe is presently in a state of expansion. Okay, on that note, that's it. Physics 20 is done. Farewell, and see you in Physics 30.